All right, let's take a look at the rest of the answers from the second review sheet from last week. I think you turned in a couple pages of it. So I think the first 20 answers were already up, and you probably already checked those, hopefully. And now it's just a matter of making sure you're good on everything else. I didn't get a single question submitted to any problems on here. On the other hand, I did have about half of you that turned it in on number 21 just wrote, yeah, I got stuck on this problem, which is great, except that we have help sessions almost every day. So if you get stuck on a problem, what you're supposed to do, you're supposed to come to a help session and ask for questions. I had about 4 people who did that, and they were able to work their way through that problem. If you don't, there's really no excuse. So you got the 4 days that the packet had been posted, 4 different opportunities. You got email, you've got messages that you can post on Google Classroom. So if you're not seeking help, then you really got to think to yourself, should I be in an honors course at this point? I mean, I know that these are difficult times, but if you're in an honors course, be an honors student, is all I'm saying. Problem number 1, pretty straightforward. The central angle and the arc were 1 to 1. And then if you subtract 80 from 360, you have the remaining 280. So you set the 10y plus 120 equal to that. So there's the work there. Number 2, this time we had an inscribed angle, so it was half of the arc. Now it's easier to multiply by 2 than it is to divide by 2. So what I did is I multiplied the inscribed angle, as you can see here, by 2 to set up the relationship. And that's how you solve for z. And then once you know that z is 15, bam, throw it in. 2 times 15 is 30 plus 40 is 70, and then you take the 70 and the 165, subtract that from 360 to get the remaining arc over here, which turned out to be 125. Number 3, 3 arcs make up a full circle. Well, that means that those 3 arcs have to add up to 360. So we set up the equation down here, and with a little bit of algebra, we find W is 22. We plug W back in. It looks like for AB and BC, they wanted arc ABC, so we didn't need the AC part of it. So we just substitute, simplify, and 242 is the answer there. Number 4, those diameters are going to be really helpful. You got to find them because they give you semicircles. Knowing that I've got a semicircle here, I just subtract 65 and 58 from 180 and then divide by 2 since I have an inscribed angle. Number 5 was very similar to a problem on the previous packet. It was a tricky one, but this is the second time you saw it. There's really 2 ways you could go. The quick way, knowing that we have a tangent, is to use property 10.1, theorem 10.1, which gives us a radius tangent perpendicular relationship. Now they didn't give you the radius, that's what made this so tricky. So you add the radius, and then suddenly you have a right triangle with only one missing angle, which is 56, which is the central angle, and then that kind of finishes off the problem for you. The other way that you could have done it is to extend this segment. This segment right now isn't really much of anything. It starts outside the circle, but it does end at the center. So what that means is if I extend it, I get a secant segment, and then I can use the theorem 1013, the secant segment relationship, which told us that the big arc minus the little arc x is equal to 34. Oh, and divide by 2. So that's the work that you see up here. So check that out a little bit. This is doing the right triangle method, where we get that 56 pretty quickly, and then just double the inscribed angle to equal that. You could also take half of 56, which is 28, and set 4a minus 16 equal to it immediately. I think either one of these 2 methods down here works probably quicker than using Theorem 1013. Number 6 is a direct application of Theorem 1012 to chords intersecting. So the angles formed is the average of the arcs intercepted. So first of all, yeah, we probably want to use linear angles to get n, but then we just average m and 120. We average those to get the 100-degree angle. Number 7, I have congruent chords. Congruent chords means congruent arcs. So I take the 2 arcs I do have, subtract those from 360. 220 split in half is 110. So each one of these chords or arcs is 110. Set your arc equal to 110 and you're done. Number 8, same type of thing, except this time we didn't know the chords were congruent. But once I saw subtract the 3 known arcs from 360, I find that I get 116. And congruent arcs tell us congruent chords. That was an if and only if theorem that we're applying there. If you're wondering what theorem, I believe it's 10.3. Congruent arcs are defined by congruent chords. And so that's how you know that 2q plus 2 and q plus 8 have to be equal. Number 9, I have these 2 inscribed angles, this one and this one, and they're both intersecting the same arc. So by theorem 10.8, they have to be congruent, which means that the angles have to be equal. Once you know that x is 36, we can substitute that back in to get the value of the angle, which doubled is equal to the value of the arc. Number 10, parallel chords intersect congruent segments. So after I subtract the 2 known arcs from 360, I know that the remaining 2 arcs have to be congruent. So that's what I did here. I subtracted and divided by 2 to get 58. And then I can just set 7y minus 12 equal to 58 to solve for x. Number 11 is a direct application of theorem 1011, where the angle formed by a chord and a tangent is half the arc that's intercepted. So basically, if I multiply this angle by 2, I get to the arc, which is exactly what I did right here. Number 12, we're talking about theorem 1012 again, where the angle formed by 2 intersecting chords is the average of the arc. So I averaged 41 and 53, and I got 47. And once I know that this is 47, I use linear angles, subtracting from 180 to get angle 1. Number 13 was a direct application of theorem 1013. When you have 2 secants, 2 chords, or I'm sorry, 2 secants, 2 tangents, or 1 of each, they intersect a circle, the angle formed is the difference. So notice how this time we're subtracting of the arc. So big arc minus little arc divided by 2, and you can see how the algebra works there. Number 14, same thing. This time it's a secant and a tangent instead of, this one was 2 tangents. I guess another way you could have solved this that would have even been easier, whenever you have 2 tangents, you only have 2 arcs. So I guess in this case, these 2 arcs could have just been added together to equal 360, and that probably would have been a slightly quicker way, maybe only 1 step quicker, but a quicker way to get the same answer. But on this case, you really had to use that theorem where you do big arc minus little arc is equal to the angle. I didn't know what the big arc was, but I knew there were 3 arcs total, so I subtracted 92 and 110 from 360 to figure out what the missing arc was, 158, and then I could do the average right there, or the difference, half the difference, 158 minus 92 divided by 2 to get the angle. Once I knew the angle was 33, pretty easy algebra, set it up. Number 15. This time we're doing distances, so this is theorem 1014. When 2 chords intersect, the segments of the chords have the same products, and so 10 times x minus x plus 1 is equal to 5 times 12. And there's the algebra. Number 16, When you have secant segments in a circle, it's the secant segment multiplied by its exterior segment. Same thing with the other one, the full secant segment multiplied by its exterior. So 5 times the whole thing would be 8 is equal to 4 times, and the whole thing would be x plus 4. And once again, you can follow the algebra for yourself on the screen. Number 17, when a tangent and a secant intersect outside of a circle, you do the same thing with the secant. You do the exterior part, right? Exterior part, x plus 2, times not the interior part, but times the whole thing. And x plus 2x is 3x, 2 plus 5 is 7. So there's the whole thing, 3x plus 7. You multiply those two things, but because the other one's not a secant, it's a tangent, there's only one piece, you have to square it. Be careful when you square 2x, because it's not just 2x squared, it's 2 squared times x squared, or 4x squared. Very common mistake is people are so excited about squaring the variable, they totally forget that you got to square that coefficient too. Okay, so be careful about that. By the way, when you solve a quadratic and after you set it to equal to 0 and factor it, make sure you check. -1 almost worked, because -1 plus 2, 2 times -1 plus 5, those would have both been positive segments, but 2 times -1 is not. So see ya. Number 18, arc length. So fraction of a circle. Arc AB is linear with 150, so 30 degrees, and 30 out of 360 times 20 pi turns out to be 5 pi thirds centimeters, or approximately, if you multiply by 3.14, 5.23. Number 19, 360 minus 240 is 120, so 120 times 2 pi r for the circumference is equal to the length. They gave us 64 pi. I'll let you take a look at the algebra there as you solve for r. The key there is to use reciprocals. Okay, reciprocal of 2/3 being 3/2. And then number 20, I had to plug -3 in for h here. And notice how minus a negative is really +3. Plug 2 in for k, so x plus 3 squared plus y minus 2 squared, and then 5 squared is 25. So there's your answer after you plug things in. And so -3 plus 2, the center would be here with a radius of 5. So that should have been kind of what your circle looked like. Number 21. This is the one so many people didn't really get. So notice how we give you a tangent line, and we give you a common chord. What are we going to do with those? Well, the fact that this is tangent is going to give me a couple tangent segments. So CM is a tangent segment. DM is also a tangent segment. Now the chord AB isn't helpful because it doesn't connect to M. So I'm going to go ahead and make that into a secant segment and go all the way to M. Okay. We have a theorem, 1016, that deals directly with this situation. And what it tells us is that this length right here squared has to be equal to this external length times the entire length of the secant segment. So the way that we're looking at it is it would be CM squared is equal to MA times MB, right? So that's a relationship you can get. Going to circle Q, you can get a very similar relationship, because we have, it turns out, the same exact secant segment, MB. So MA times MB, except this time the tangent segment is MD, so it's equal to MD squared. And so by just applying Theorem 1016, we get these two lovely relationships. Notice here that they're both equal to MA times MB. They both have that same relationship, which means we can use the transitive property. When two things are equal to the same thing, we can set them equal to each other to set CM squared equal to DM squared. By then taking the square root of each side, you could just say take square root of each side. You could say, I use radical property because we have like addition property, subtraction property, etc. of equality, but whatever, we're good. Now, I probably should have added a step right here because equal segments don't mean midpoint. Midpoints are defined as a point that divides a segment into congruent pieces. So I really should have said that because of the definition of congruent segments, CM and DM are congruent segments because they have equal length. I probably should have added a step in there. But yeah, I now have two equal segments, and so by the definition of a midpoint, we're going to get what they asked us to prove. Okay, so this wouldn't be in this chapter unless they wanted to use these theorems. So try to use those theorems. Number 22, you really didn't have to find the midpoint because, if this, we know that the perpendicular bisector is going to go through the midpoint, but it's also going to go through the center. So really, once you found the slope of the chord was -1/7 and the opposite reciprocal was 7, you really could have just used 7 in the center point, which we already have, and then you wouldn't have had to find the midpoint. It would have gone a little faster. You would have got the same equation. This one, though, there's, boy, you could have actually really gotten this one super easy because um, it didn't say, it just said you can't go through M or N. So, you can't do a diameter that goes through ZM and ZN, but I could have done a horizontal line, and that would have been really easy. That would have been just Y equals -6, or a vertical line. That would have been, X equals 4. That would have been a really, really easy ways of doing that if that was something that you really had to do quickly. Number 23. Here's the deal. We have a theorem 10.9 that tells us that a right triangle inscribed in a circle, that its hypotenuse must be a diameter, and that's because that right angle, that's an inscribed angle, is going to create a 90-degree arc, right, or a 180-degree arc. 90 times 2 is 180. Well, 180 is a semicircle, and so when I have this this right triangle, I get the diameter as the hypotenuse. That's what the Carpenter square gives me. What most people didn't do, though, is they didn't say, well, great, that all that gives me is a diameter. It goes through the center, but it doesn't tell me which one of these points is the center, right? So that's not enough information. Some people say, well, I'll find the midpoint. Well, that's great if it's on a grid and you know that, R is a certain value and S is a certain value. You don't have coordinates for R and S. How are you going to find the midpoint? Um, you're only allowed to use the Carpenter square. So how can you do that? Well, it didn't say we could move the Carpenter square. And so if I pick any other point on the circle, like maybe let's say pick that point right there, and recreate the same scenario, where I have another right triangle, okay, I can use my second hypotenuse, which would be going from here to here. And now I have two diameters. Well, that means the center has to be at the intersection. The center would have to be right at that point of intersection. So that's how you could find the center of the circle. It definitely has to do with the first, the first triangle, but you need to use it twice because you need to pinpoint a single point. And then the last page, those of you that did this looked like you did a pretty nice job. Some people need to show more work. Once again, we've been doing equations of circles for a week now. So if you are struggling with how to do this or how to complete the square, and you still have not come in or come to the help session to ask questions, or you still haven't sent me a message, then there's no way you're going to get help. There's no way. You've got to do something proactive to get help. Most of you guys, I think, completing the square and finding these equations of circles has become a really simple thing. So that's good. There should be some pretty easy questions on the quiz tomorrow. If you do have follow-up questions, look at that tiny little circle on number 27 there. If you do have any follow-up questions, let me know. But like I said, nobody asked anything specific. So that's as far as this goes. Adios.